What's up, mathematicians? Welcome back to our lesson on area. In the last video, we introduced this idea of area based on the square unit. We talked about a couple formulas for area. And in this video, we're going to use one of those formulas to find a solution to one of those measurement challenges from the first lesson in this unit. So first of all, just really quickly, the measurement challenge that we're going to be finding a solution to is this one right here, the fence maker, where I said you've got two plots of land, plot A and B, and you want to replace the fence between them, which is this orange line. But instead of making it crooked, like what you see here, you want to just make one straight fence. Replace that crooked fence with a straight fence. But at the same time, you have to keep the areas of the two plots of land to be equal to what they are right now. So that was the challenge. We can use one of our area formulas to figure out a solution to this problem. Okay, but before we get to that, one thing I need to point out, you may not have realized it, but we have made yet another assumption. When we looked at this idea of the area of a parallelogram, the formula for the area of a parallelogram, we made another implicit assumption in that formula. We assumed that if two lines are parallel, they must always be the same distance apart. Okay, now we're going to add a connected assumption to that. Okay, so just to refresh our memory, here is the formula for the area of a parallelogram, and it relies on the fact that the height here is equal to the height here. In other words, these two parallel lines, the distance between them must be the same here and here. And basically, we're generalizing that to say the distance between two parallel lines is always going to be equal. So a connected assumption we're going to make is this. We're going to say that given a line, so we can see the base of this triangle. This is our line. In fact, let me label the points here. So given the line A, B, and then a third point, some other point that is not on the line, that's going to be this point up here. So I'll call that C. Okay, so given a line, in this case AB, and given some point not on the line, in this case C, we can draw a line parallel to this line through that point. That's what we're assuming. And moreover, we're assuming that there's just one. And this kind of makes sense, right? That there would only be one of these. So let's go ahead and draw this, and I'm going to draw it in a different color. And so through this point C, I can draw a line parallel to the line AB. And we're going to go ahead and say there can only be one of these lines through this point parallel to this one. And if you think about that, you know, that makes sense, right? I mean, if I went at sort of an angle like this and I drew another line, it seems like eventually this line would have to meet with this line, and therefore it wouldn't be parallel. So we can draw just one line parallel to the given line through this point. Now, an interesting consequence of this is that I can pick any point on this line. You know, for example, I could pick a point right here, and I could draw a triangle using that as the vertex, but keeping the base of the original triangle. And so here, I'll draw that in like this. Okay, so now you see this new triangle. I'll call it ADB. So the triangle ADB must have the same area as the triangle ACB. How do we know that? Well, they both have the base AB, and they both have the same height because the distance between this line and this line must always be the same. Even though in the case of this one, it'll drop down to a point off of it, you know, we can always extend this line, you know, past the end of the triangle. I can extend it here, I can extend it there. And so if you drew that perpendicular down, you would still end up with the same height for this triangle. So this is an interesting thing that results from the area, the formula for the area of a triangle, which of course was that the area is equal to 1/2 times the base times the height. So the direct result of that formula is that I can put this point anywhere on this line and set that to be the vertex of the triangle with the base AB, and all those triangles will have the same area. We can use this fact to solve the problem of the fence maker. Before we actually do it, I want to show you a little animation I made in Desmos. And so let's hop over to that. Okay, so here is a little sketch I made in Desmos. You can see the triangle here is in green. The height of the triangle is in blue, and the line parallel to the base through the vertex is this red line right up here. Now, of course, if I change the height of the triangle, oh, and by the way, the area you can see is calculated right here. Area equals 7.5 for the current setup. Okay, so if I change the height, of course, it's going to change the area of the triangle, right? So here I am changing the height, and you can see right down here, the area changes, and that makes sense. Okay, so let's set the height back to 3. Once again, or similarly, if I change the base, of course, it also changes the area of the triangle. So here's a longer base, we see a bigger area. Here's a shorter base, we see a smaller area. Okay, so I'll bring this back to, where did I have it? It doesn't really matter too much, but I'll set it here at 5. But now this slider here enables me to change the vertex point of the triangle. And so you see I can set it to different places on that red line. And it doesn't matter where that vertex is, the area stays the same. Here I can animate it, and you see it slide back and forth there. The height of the triangle, that blue line, stays the same regardless of where that point is. And because of that, the area stays the same, because the area of a triangle is just 1/2 times the base times the height. So Desmos, by the way, is a great tool for playing around with these types of things and many other things as well. I do encourage you to familiarize yourself with the program if you're not already familiar with it. And I'll include a link to that sketch in the description so you can play around with it, mess around with it, and maybe make your own similar tools. One other thing that I will say connected with that is, in order to find you can prove something similar about the area of a parallelogram. And in fact, you might try creating a Desmos sketch that does that enables you to look at different parallelograms with the same height and verify they have the same area. So that's an optional thing, but there'll be a problem in the homework, the practice problems, about parallelograms. But now let's turn to that fence maker problem. Okay, so here is a diagram of the problem, and as stated in the description of the problem, what we want to do is replace this crooked fence here with a straight fence, but do it in such a way that the areas of the two plots of land do not change. So this area will stay the same, this area will stay the same. Now, of course, some of the land from this area will end up on this side, some of the land in this area will end up on this side. But at the end, they have to have the same area that they do right now. So what you can do is you can just recognize that, well, wait a second, we can turn this into a triangle, right? And so let's go ahead and draw in, I'll even draw an extended base here, okay? So there is a line, and right here is the base of a triangle. Now we can also draw a parallel line to the base. And I'm using the dots on my dot grid paper. If you don't have that, you can always use a compass and a straight edge if you know how to construct it, or use, there are other ways to do it as well with, tools like a triangle with a right angle. But the point here is that I need to have a line parallel to the base of the triangle that goes through that point right there. Now, all you need to do is, you actually have two options here. You could connect this point to this point with a line, or you can connect this point to this point with a line. But basically, the fence maker has to, before tearing out this fence, they would want to mark 2 points. So we'll put one right there, and we'll put the other one right here. And then they can tear out that orange fence. And once that's torn out, they can draw one straight fence, replacing the crooked fence from this point here to this point here. So let's draw that in. So there it is. That fence will keep the areas of these two plots the same. And the reason is because it's a triangle with equal height. So like that height right there is the same as the height of this orange triangle here. So let me draw this in here. Okay, so this orange height, right, is the same as this purple height. And then the bases are also the same. This distance, this is the base of both triangles, and therefore the two triangles are equal. The orange triangle you see there, and I could draw the rest of the purple one in here. But yeah, it shares that base right there. So that is one way, probably not the only way, but that is one way to solve this problem. Okay, so before we wrap up this video, let's take just a minute to revisit that list of assumptions, since now we have made it even longer. So here we go. These are the three that I mentioned in the previous video, right? Similar triangles exist and the sides are proportional. All right triangles have the same angle sum. And finally, squares and also rectangles exist. Now we're adding two more sort of connected assumptions. The first one is this: parallel lines are always the same distance apart. Might seem obvious to you, might seem like, yes, of course that's true, but we have not proven it, so we are assuming it. We needed this for our formula for the area of a parallelogram. And connected with that, we decided to add this assumption right here. Okay, given a line and a point that is not on the line, you can only draw one line through that point parallel to the given line. Okay, now I know that's a bit of a mouthful, but we did use this assumption in connection with the first assumption to solve that fence maker problem. Now, this last one actually has a special name. I'll mention it now, although we'll get into it more in future lessons and future units. It's actually called Playfair's axiom. And in case it's too much of a mouthful to see all the words, here's a diagram, right? So given a line, in this case the line AB, it's possible to draw one and only one line through that point C, a point not on the line, that is parallel to the given line. Okay, a little bit of a mouthful, but with a diagram, pretty easy to understand. Okay, so that will wrap up this video. We'll have one more video in this particular lesson where we'll look at how we might go about finding the area of a general quadrilateral. We'll take the Egyptian approach to that one as well. At least we'll take a look at it. And as always, thank you so much for watching. Really appreciate it. If you did learn something today, please do like and subscribe, and I'll see you in the next video. Bye-bye.